Oh, I thought you'd gone quiet, so you wanted me to start again. And now as soon as I start, you all start talking. Well, that's going to sound good on the recording. I wonder if I can break Echo 360 if I do something extremely loud into that microphone. Alright, so here's a scenario. We've got a virtual memory. It's a trivial one. You know, the memory's only got 4 page frames. The process itself has 6 virtual pages, or 6 pages in its address space. And these accesses here are basically references to pages. So at some point, maybe this is the fact that it's a high address, a high virtual address means that it's setting up the stack. 0 means that it's a low address, so it might be referencing the main program or one of the other functions. So, first thing that happens, we refer to something in page 5. We look at the page table and see page 5 is not loaded yet. So, we need to find a free page frame to put it in. Well, that's pretty easy because everything's free. So we can put page 5 from the virtual address space into that page frame and tell this that page 5, virtual page 5 is in memory page 0 and we accessed it at time 0. Let's try and distinguish these numbers. Okay, so virtual page 5 is in page frame 0 and it was last accessed at T0. Right, next thing. At T1 we examine page, or we reference page 0. So we look here, is page 0 currently loaded? No, it's not. So we need to find a slot in memory where we can put it. And it turns out that since everything is free, that makes life easy. Okay, the next few references are also to page 0, so all we need to do is update. So T2, last accessed T3. And then we access page 5. So that's, what are we up to? T4. Now so we've done all of that stuff up to there. Now we make a reference to page 1 in the virtual address space. So our mapping function goes and has a look here and says page 1 not currently loaded. So we need to find a page frame in memory. We can use this one and we can allocate that to page 1 of the process, and that happens to be frame 2. And this was at time T5. So that's the scenario at that point. We do another reference to page 1, so it was last accessed at time T6. We then refer to page 5, T7. We then refer to page 1 again, T8. We then refer to, well, what are we up to? Oh, it must be this reference here. So last access T9. So now we've done everything up to that point. Right, next thing to look at, next reference is page 2. Alright, we go to the page table, page 2 not currently loaded, so we need to load it, which means we need to find a free slot. There's one left. So this can be page 2, allocated to page 2, and that happens to be frame number 3. And it's T10. What's the access? Right, the next thing that happens, we're up to here now, is we make another reference to page 2, so its access time gets updated. And the next thing we do, now we get slightly interesting, page 3. Alright, page 3, we go to the page table first. It's not currently loaded in memory. We look for a free page frame. There aren't any. So now we have to decide which one we're going to dump. So, and this one works out rather unfortunately, that the least recently used page frame is this, the least recently used, least recently used page frame is page 0, virtual page 0, which was last accessed a long time ago, way back here. So we decided, all right, that's it for you. So you get written out and you get replaced. In fact, we can flag it as having been written to disk. So let's assume everything's going to be modified, so we have to save it. And page 3 now takes over frame 1 at time 12. And so we need to indicate that one is now occupying page 3. In fact, we don't even need to remember that. And we probably don't need to remember the T3 either. We just need to remember that page 0 has been kicked out of memory and a copy of it has been written to disk. Alright, so what was that? So that was page 3. Next reference is to page 0. Damn, that was the one we just kicked out. So if that kind of thing happens too often, that's when you get thrashing. So page 0, not currently loaded in memory, we know it's on disk. We need to have it in memory so that we can do something to it because we've just made a reference to it. So we need to find a slot. There are no free slots. So we look for the least recently used. We can forget about that. And the least recently used was page 1, okay, which happens to be in frame 2. So we grab frame 2, we kick page 1 out, and we install page 0 there. And it's T13 was the last access. So, what was it? Page 1 got the boot. So now it's been written to disk. The next reference is page 0 again, which is nice, so it can stay there. Jumped ahead in time. And the next reference is to page 5, which is also currently loaded in memory. But we update its access time, T15, and so it would go on like that, okay? Alright, let's take a look at the one down here, which is, I think, a little bit different. So remember, all the page frames start out as free, or we assume they do. Right, first reference is to page 0 in the virtual address space. So that's not currently allocated anywhere, so we'll find the first free page frame, which happens to be frame 0, and we'll install page 0 there. And that was it. Time 1 was the last access time. Next access is to page 5. Once again, we look in the page table. Page 5 isn't loaded anywhere, so we need to allocate a free frame for it. There is one at frame 1. So frame 1 is now occupied by page 5. Next two references are to page 0, which is already loaded, so all we have to do is update its access time. 1, 2, 3, 4. Next access is to page 5 again. Also loaded, so once again we don't need to do anything. Alright. Next reference is to page 1, generates a page fault because page 1's not loaded in memory, so we need to find somewhere in memory where we can put it. Fortunately, there's still a free page frame. Page 1. So that's been loaded in frame 2 at T6. Next reference is to page 5, that's already in memory, so we're going to look here and say go to frame 1, and we've got all of the data for page 5 that we need there. and that's a new access. The next access is to page 1. Next access is to page 2. Oops. So we're up to there, we've done all of that. Page 2, not currently loaded, so we need to find a frame to put it in. Frame 3 is free. Try saying that fast. Frame 3 is free. Frame 3 is free. Right. So now we're up to here. Next reference is to page 4. Oh dear. No room here. Page 4 is not in memory, so someone has to get booted out. So we look for the page frame that was least recently used, and it turns out to be this one here. It's got the oldest access time, and so that's the page that gets booted. It should have said frame 0, I'm not sure what it said. So this now inherits, well, this gets page 4, and I assume it's time T10. Next page access is to page 3. Once again, page 3 isn't currently loaded, so if there was a free frame, we could use that, but there's not, so we need to evict somebody, and it looks like page 5 is the least recently used one, so that's going to get the boot. And we can now use frame 1 for page 3. That was T11. Alright, you can see this one I kind of a little bit engineered to demonstrate the working set approach. So here we've got a few pages. You can think of page 0, 1 and 5 as being the working set early on in the program, and we then switch to a working set which involves these pages later on. Unfortunately, page 5 is going to ruin things a bit. But alright, so we've got page 3 loaded into frame 1, and then it's referenced again straight away, so all we need to do is update the access time. We then reference page 4, so we update its access time. We reference page 2, update its access time. And what we're hoping is that we're always going to make references to pages that are currently loaded in memory, so the operation's relatively cheap. Unfortunately, the next reference is to page 5, which is currently on disk, so we need to evict one of these pages, and we find the least recently used one, which is virtual page 1, currently in frame 2, so we can repossess that and use it for page 5. So you can see that page 5 came back, but it went back to somewhere different to where it was before. That doesn't matter, because all of the references to memory addresses go through the page table. So you'll always come here, first of all, once you've worked out which page it is, and then you'll go to the appropriate location in memory, add on the offset, and you get the absolute physical memory address. Alright, so where were we up to? Oh yeah, we just did that. Right, the next reference is to page 3, so that's in memory. We update that. Next reference is to page 2. We update that, and we keep going like that. Okay? So, virtual memory, swapping, if you like, swapping pages, page replacement, all contributes, thanks to the working set model, to being able to hold a relatively small part of a process in memory, and the process will just keep running without too many page faults and page swaps. Okay, so I've talked about process page tables, and process page tables are potentially problematic because the process space of a process is potentially very large, and if we need to represent each of the pages in the process's page space as part of the page table for that process, it means we're going to have a very large page table. So that's a potential problem. One strategy that we could use is it's almost a little bit like the working set for a page table. So we have a page table, and all it holds is a small number of pages which we hope is going to cover the working set. So when you make a reference to a virtual page, you run it through, so you've got a virtual page number, you run it through a hash function, and that gives you an index into the page table. So it's no longer the page number is a direct index to the page table. We have some function that squashes the references into a relatively small number of indexes. So here we've got potentially n page numbers. Here we've got a small number of page table numbers. So the hash function is taking a page number and compressing it into that space of indexes. Alright, so if it turns out that we've made a reference to virtual page 15 and the hash function takes us to page 0, then we can go straight to the physical page in memory as before. So how big do we make this thing, and how smart does this hash function have to be? Sure, they're things that need to be worked out, and maybe we'll look at them in tubes or something like that. But anyway, this is a potential approach to dealing with the problem that we don't really want to have a page table with n entries in it, where n is potentially a very large number. Another commonly used strategy is to have multi-level page tables. So we have a first level page table which handles a number of pages. So in this case, the first entry in this level 1 page table deals with all of the pages in the range 0 to 7. And what it contains is a link to a page table that handles those pages. The next entry in the level 1 page table handles pages 8 to 15, and it will contain an entry to another page table, another level 2 page table. And entry number 2 handles all of the pages at the top end of the virtual address space from n-8 to n-1. Okay? And you might say, how does that solve anything? You've got this level 1 page table and you've got all these level 2 page tables, and the level 2 page tables are going to have to cover all the pages anyway. The trick is that a lot of these level 2 page tables will never actually come into existence. Because if you think about the address space of a process, you've got the code down the bottom, you've got the stack up the top, you've got the heap in the middle or down towards the code, and you've got this big gap between the stack and the heap, which is rarely totally occupied, and if it is, it's likely that there's something wrong with your program, either a memory leak or too many levels of function call. So a large amount of the virtual address space is never actually going to materialise. So perhaps we'll never actually need to reference pages 8 to 15. And if that's the case, then rather than having is that 24? Yeah, rather than having a page table with 24 entries in, a single level page table, we've now got 2 page tables each with 8, so we've only got 16 entries. Page tables with 16 entries. So that's a saving. Admittedly, you've got the overhead of the level 1 page table. But if you think about what's going to happen in a realistic example, you may have 100,000 pages potentially available in the process address space, and if you're only using the first 100 and the last 100, then having page tables just for those is going to save you a lot of time. So this works because in most programs we don't use the entire virtual address space throughout the life of the process. One final trick that virtual memory allows us to pull is that if we've got read-only pages that hold stuff that's used by many processes, and the classic example is library functions, if we've got code for the library function loaded into memory for one process to use, there's no particular reason why another process couldn't make use of that same piece of read-only code. Now, of course, you're relying on the fact that the shared library code can occupy some space. Is going to appear somewhere in the virtual address space of your process. So, page table for process 1 can say, hey, if I need to make 1, 2, 3, so the printf function happens to be in page 3 of my virtual address space. And if the page table entry links to this page frame in main memory, that's where the printf code is. And let's say this process refers to the printf function, or it says the code for the printf function is in virtual page 2. Then that could also link to the same page in main memory. So we'd only need one copy of the printf function to be loaded into main memory. So that's clearly going to save time or save space. As I mentioned before, if you do things that way, you need to be a little bit careful. You want to, if you've got multiple processes, and if you think about something like printf, there's a chance that there'll be dozens of processes linking to the printf code. You want to make sure that that's not a page that gets booted out as part of page replacement. So anyway, that's a trick that can be used because of the fact that we're doing this virtual memory management. Alright, that's enough for virtual memory. Let's take a look at another very important concept in the operating system space, the notion of a process. Right, so what is a process? It's basically an instance of a program, if you like, the runtime embodiment of the program. So if you've got a piece of code, if you've got a.out, you can have two X terms open and you can be running a.out in both of those windows. So you've got two separate processes, even though it's one piece of code. So a process represents a running program, so there's a whole lot of information that, bound up in that. So we've got the program code, obviously, the global data. We got all the dynamic information, the heap, the stack, and importantly, if you think about the execution of a program, where are we up to during the execution of a program? That's defined by the program counter, okay, which we have seen as the PC register in MIPS. And similarly, if you imagine that we've compiled all these programs, our C programs up to run on MIPS, they're going to have a bunch of register information that defines the current state of the executing process. And then there's a bunch of other stuff that gets applied to a process, environment variables and the like. So managing all of this information and being able to execute processes simultaneously is something that the operating system does for us. The other thing that it does as far as processes are concerned, all of these processes want to run on the machine and have the impression that they're the only process on the machine. So they're executing and they're going to run until they finish. They're going to do their computation, whatever computation they have to do, and eventually they'll say return 0, and they'll be done. And as far as the process is concerned, that's what happens. In reality, of course, processes are going to be swapped in and out, so the process will run for a while, it'll stop for a while, it'll come back for a while, it'll stop for a while, it'll come back for a while. But as far as the process itself is concerned, it just starts at start of main and goes till it does the return 0 statement. Similarly, we've already seen virtual memory provides each process with a view of the memory space from 0 to n-1 pages. That's what it sees, that's what it manipulates. But we know that the reality underneath is that these pages are all over the place. Some of them aren't even loaded in memory at any particular point in time. So this notion of control flow independence is something we want, but the reality is that there are multiple processes running on the machine, not necessarily at the same time. And here, in all this discussion, I'm assuming a single CPU system. Nowadays, most machines have got multiple CPUs, but on a system that has a single CPU, a process can use the CPU for a while, and eventually, before it's finished its work, it'll get booted out, and some other process will run, and it'll do some work for a while, and then it'll get halted temporarily, and then another process can run. It'll run for a while, it'll get halted, and then process 1 can have another go for a while. And the overall impression you get from a scenario like this, even though there's only one process running on the machine at any given time, is that we've got multiple processes running simultaneously on the machine. So what's the nature of this preemption? So I've said a process can be preempted. A couple of ways that can happen, possibly on the next slide, yes. It runs for a while, and the operating system decides, all right, you've had enough of a go, give someone else a go. So that process gets suspended. Another thing that can certainly preempt a process is if it initiates some I/O. Typically I/O, and especially to external devices, is a very long duration process. So there's no point having that. Once the process says, I want to send some stuff to the disk, there's no point this process sitting in memory trying to do something, because it can't do anything until all of that information has been written out. So you may as well, as soon as you initiate an I/O operation like that, suspend the process. And it can come back later on when the I/O is done. So what happens when a process is preempted? We've got to save the entire state of the process. So the process knows where it's up to. We've got the program counter, we've got the contents of all the registers, and we've got the processes address space. Some of the address space is sitting in page frames in virtual memory. We don't necessarily have to write them all out. They can just stay there, because when the process comes back, if those page frames haven't been replaced, then they're still sitting there waiting to kick up again. The other thing we need to do, so there must be a notion here that a process has a state, and this state is stored somewhere in the operating system. So in Linux there's a process table that contains information about each of the currently executing processes. One of the pieces of information it will hold is whether the process is suspended waiting for I/O to finish, whether it's just suspended because it used up its last time quota, whether it's currently executing, whether a user has suspended the process by doing Control-Z, for example. And it'll be placed on a queue so that it can be restarted. So if a process is preempted simply because the operating system thought you've had enough of a go, right? no particular reason why you couldn't keep going, so you just go back on a queue, and the next time there's some CPU available, you can be scheduled to run. So when you resume a process, all of that dynamic state has to be restored. Potentially that involves loading up the program panel, loading up all the registers, the kind of thing that we've been doing with MIPS. And the process just starts again where it left off. And that's how we give the process the impression, I start, I do my computation, I finish, and as far as I'm concerned, I'm the only process in the world. Alright, so being a bit more specific about processes on Unix and Linux. So a process runs in an environment, and the environment on Unix and Linux, there's a whole bunch of stuff available to a process that's all made available when the process starts executing. So the standard in, standard out and standard error streams are all given to a process when it starts running. argc, argv, obviously we've seen. The environment pointer, so in fact, C main programs have actually got 3 arguments. Most of the time we just use 2 of them, but you've got argc, argv and envp, which is another array of strings that you can use to, that can provide information that the process can use to configure how it runs. Okay, so you can look at the stuff in the environment pointers and decide what to do. So envp is basically exactly the same data type as argv, except that we don't have an envc counter. I think the way it works is that the final entry in the envp array is null. But otherwise it's just a string, an array of strings. Other information that's available to a process, or kind of, if you like, forced on a process, when a process is run by a particular user, and that determines the kind of things that that process can do. So if a process runs and it's running as me, and it tries to open a file in your directory, and you've said no one else but you can open that file, then my process has to somehow know that it doesn't have permission to open that file. The only way I can work that out is if it has an idea of who the process has been run by. So fopen would be able to work out, okay, and this is all going to happen at a much lower level than fopen, but when I invoke fopen, it knows who I am, it can look at the object that I'm trying to fopen and decide whether I have the right permission to do that. So that's at the user level, and similarly, Unix access control involves a user and a group. So which group did I run this process as is important as well. And there's a whole bunch of other stuff. So stuff that comes out of a process, we've obviously seen the standard out and standard error stream. So printf goes to standard out. And at the end of your program, of your C main program, you do return 0 or return exit success. Okay, so that information is sent back to the environment. Whether the environment actually makes any use of it or not is up to the environment. So if you're writing a shell script, then you can invoke a process and you can check whether the process was successful, and you could use that to determine how the shell script should behave in the future. Okay, so Unix gives you a whole bunch of ways of manipulating or examining processes. So the shell is the obvious one. You run a shell. What's the purpose of the shell? Is that you type the name of a command, and that command gets executed as a process. Assuming you can find an executable file somewhere in your command path with that key, it will execute it. It'll create a new process for the execution of that file. If you want to find out about processes, you've got PS and W and top. And if you want to send a signal to a process, there's the slightly unfortunately named command kill, whose goal isn't necessarily to kill anything, but I think the original intent of sending signals in Linux was to, or in Unix, was to kill off processes, so that's the name that we've inherited. Alright, so those things exist at the command level, so you can run them from the shell. The system calls that are relevant to processes. Unix has slightly interesting philosophy which has been inherited by Linux. The way new processes come into existence in the system is through the fork function call. So what fork does, it kind of creates a clone of the current process. So it makes a new process which is a clone of the current process. And there's exactly one difference. So, I should have said, the cloned process is a child of the original process, and that relationship is also part of the process information. So a given process knows who it's a child of. But the one difference between those two processes is that the parent process, now I've forgotten which is which. Let me just check. And I'll say the wrong thing. So here's where you can find out all about fork. Oh yeah, I can actually work it out from there. Alright, so the parent process gets given the process ID of the child process. So that's the return value from fork. The return value from fork for the child is 0. Okay? So we've got these two processes. We've got a process that clones another process. They're both executing from the same spot. They're both going to return from the fork function. One of them gets a value back from fork, which is the process ID of this one, and this process here gets the value 0 back from the fork. So they can determine what to do based on that information. So you might say, well, that's all very nice. I can clone processes, but what if I want to run a different process to the one I started with? Well, the thing that you do is you do a fork, and then the child process transforms itself into some other process, which is what the exec system call does. Once upon a time, it just used to be called exec. Nowadays, it's called exec VE for reasons that I don't know. So it transforms a process essentially. It says, all right, here's a process. When I do an exec, I invoke another process which takes over that process ID and starts executing. Other things you can do with processes is a parent process could wait for some information or for the status of a child process to change. For example, the shell is just going to sit there. When you invoke a command, the shell just sits there and waits. When the command that you invoke finishes, the shell gets told about that, and then it can continue its execution by printing another prompt. There's also kill available at the system call level, and there's a function which I'm sure used to be called just plain old exit back in the good old days. Now it's called _exit to terminate a process. It doesn't just stop it running, it also does a bit of cleaning up, like it will close all of the open file descriptors, which might involve flushing stuff to output streams, and so on. So it does a bit of cleaning up before the process eventually stops. And of course, we saw from before that all of the virtual memory that's in use for that process, or all of the page frames that are currently in use by that process, would become free. Alright, so let's play with Unix process stuff. How do I know what processes I'm running? And this is something that is occasionally useful in the lab when you've left something running and you haven't realised. P.S. Simply, phew! That's because I've got all these windows currently running all over the place, including, oh look, I'm SSH to Williams. Right, so these are all the processes of mine that are running right now. In fact, let's see, so if I ran another one, so I just run VI, and I suspend VI, and I do PS, then this new process appears in the process list. But yeah, I seem to have a lot of bashes running. I'm surprised I've got that many windows. Interesting. Well, I guess I have. Oh yeah. Yeah, I can see where they're coming from. I seem to have, I've got tabs in all my terminals. So, and every one of them gives me a bash. Right, you can get slightly different information from PS if you go PSU. So you can still see there's a lot of bash, but there's extra information like virtual memory size, how much memory is this process occupying, and you can see that these processes aren't using any memory because they've been sitting there so long doing nothing that all of the pages that they were using have been replaced by other processes. The other thing that we can see is that all these processes have this status S, which I'm assuming means suspended because they're not doing anything. And I was trying to find the VI process, which I suspended myself, and that's got a different status, which indicates that this process was suspended not by the system but by the user. So the user put this process to sleep. How do I know what processes I've got asleep? Well, we got the jobs command that will tell you that. All right, so I can start that VI and quit it, and then it's gone from my process list. If I want to find out what other people are doing, which is a bit silly on this because I'm the only person on this machine. Oh, I should have logged into one of the other machines. But in any case, PSX will tell me about other processes from other users. In fact, let's just do that. Not as many as I thought. It must be A then. I usually do AX. Yeah. And then you can see that on a typical machine there are lots and lots of processes running. Not necessarily run by any user, but run by the operating system, like the network file system daemons. In various stages. Oh, that's interesting. There's a zombie process, which I wonder what book manager is. I don't know. All right. The other thing that you can do, W will tell me that I can't run it in this narrow window, and I'm assuming top will probably do the same. Top is useful if you want to find out who's hogging the machine, if you're on a multi-user machine. Because you can see things like percentage of CPU in use. And that's something that makes it patently obvious when one of you has submitted an assignment 1 solution with an infinite loop that just sits there using 99% of the CPU and making me think what's going on. Yeah. Thanks to all the people who submitted programs with infinite loops. Much appreciated. Not. Alright. What else? So you can use PS to find out what processes are running, top to find out the top CPU, and W will tell you who's logged in and what they're doing. And let me see, have I got any more? Oh, I do. Alright, so to implement processes on Unix, go away and play with PS and privacy in your own room. Right, so clearly there's a lot of state associated with the process, and that needs to be recorded somewhere. As I mentioned, there's a process table that the operating system maintains. It turns out that the information about each process appears partly in that operating system process table, partly in another area called the user area. And the kind of information that's actually stored in those things, every process that's created gets associated with a unique process ID. That's these numbers that you can see in the first column. I think they could be 16-bit values, and you might say, that's a potential problem. What if you've got more than 2 to the 16 processes in the system at any one time? If you do, I think your machine's being flogged to death. But what they do, they simply increment that process ID counter. When it reaches the maximum value, it just goes back to 0. Although it doesn't go back to 0, it goes back to 100 or something. And by the time it wraps around, all of the processes that had those low process IDs probably finished ages ago anyway. In any case, process ID unique among the currently active processes. There's actually two notions of user ID. There's the user who started the process, which is the real user ID, and there's the user ID which is going to be used to determine the access control stuff, which is the effective user ID. And similarly for groups, you've got the group that the process started in, and you've got the group that is going to be used to control access by group. Current working directory, obviously a process needs to know whereabouts it is, so when you do fopen, if you give a file name, it knows that you're talking relative to this current working directory. Process descriptors also contain information about execution time. Remember that I said every process has a table of file descriptors, so that information is going to be stored. And remember that that table of process descriptors is a fixed size. If you keep opening things and never closing them, you'll eventually fill that up and not be able to open anything else. Processes can control how they want to behave when they receive a signal from kill, and there's a bunch of flags that you can use to indicate that. Obviously processes need to know about pages and where they're located in memory, so a process descriptor is also going to have a reference to the page table for the process, and obviously also the process state, whether you're running, whether you're suspended, whether you're asleep, whether potentially there could be something like waiting for I/O as well. Alright, I think I'll stop there. And we'll talk more about manipulating processes, and in particular how you use fork and exec and all of those system calls next time. I said get the